Pre-Calculus Chapter 6, Lesson 1, and continuing to look at some applications now of the dot product. Another application that involves the dot product of a vector is what we call projecting a vector onto another vector. And a vector projection is simply the vector that's determined by dropping a perpendicular line from one vector onto another. In other words, if we have this vector PQ here and this vector PS, if we draw a line perpendicular from this vector down to here, this red vector, the length of this vector, is the projection of this vector U onto vector V. So this red vector is what we're interested in. This becomes very important when we're talking about forces being applied, and if the force is applied to a horizontal surface or some other surface, how much of that force actually makes it to that surface. Some of the force is deflected down the line, some of the force continues to go perpendicular, and so we have these different forces interacting. So this projection vector becomes very important. So this vector PR is called the projection of U onto V, and you'll see it noted in a couple of different ways, which we'll show you in just a moment. Now, the interesting thing here, well, let me go ahead and write this. Well, not in yellow, because that's not going to show up. So this vector is called the projection of U onto V. And the interesting thing is that if you add this vector here, this projection vector, and add it to this vertical line here, that will equal this vector here. So if we call this U sub 1 and we call this U sub 2, if I take U sub 1, which is the projection vector, and I add it to the perpendicular line from the vector onto this vector, so U sub 2, those two added together will equal the original vector. Okay, so again, a quick review. The projection is if you draw a line from one vector perpendicular to another. This new vector that's created is called the projection of one vector onto another. If you take the projection vector and add it to the vertical line, essentially making that kind of another vector, those two added together will equal the original vector. Okay? Now, the formula for determining this vector involves the dot product that we've been talking about in this lesson. The projection vector, okay, so if I have this red line here, the components of that vector, the projection vector is determined by taking the dot product of this U vector and this V vector, which is this longer one. So you take the dot product of those two over the magnitude of this vector here squared, and then you multiply that times this vector here in this direction, and that's going to give you this length of this red vector, or the components going to right here. Okay, so let me walk you through that one more time. If I have this vector here, which is the vector 5, negative 5, and I have this component here, or this vector 6, 2, what would be the components of this projection vector? In other words, what would basically be the coordinates of this point here? We can determine the components by taking the dot product of the two vectors over the magnitude of this longer vector squared, and if we multiply that number times the components of this original vector, that will give me the components of this vector here. Now remember that if I add that component then to this component here, that will equal this vector here, U. Okay, so if we're given this problem here that we're asked to determine the projection vector of U onto V, and then to write U as a sum of the two orthogonal vectors. And again, this projection vector along with this perpendicular line or vector drawn to it, those are orthogonal because they're perpendicular. We want to write this vector as the sum of this vector plus this one. So essentially what we'll be doing is this vector is equal to this projection vector plus this one. The projection vector we'll call U1, so that's what this one's going to be. And then this vector then would simply be an algebraic manipulation of this. I can determine this vector by subtracting this projection vector to the other side, so that will give me those three values. Sounds like a lot, but let's walk you through it. So to determine the components of this red vector here, which is the projection vector, I take the dot product of the two vectors. So the 6 times the 5, that's 30, plus the 2 times the negative 5, negative 10, that's 30 minus 10, which is 20. So that's the dot product of the two vectors in the problem. The magnitude of this vector, you remember, we can determine by taking the square root of its dot product. So I simply multiply 5 times 5, that's 25, plus negative 5 times negative 5, which is another 25, so that's the square root of 50, but I square it, so that's where the 50 comes from. Now I multiply this scalar number times the v vector. Whoops, move that, didn't want to move that. The v vector. So this is the v vector. So as a scalar arithmetic, you multiply this times both. So 20 over 50 times the 5 gives me 2. 20 over 50 times the negative 5 gives me negative 2. So this vector here, the projection vector, is the vector 2, negative 2. Okay? So that gives me this vector. Now, I know that this vector plus this vector, this vector plus the orthogonal vector will give me this u vector. I know what u is. That's the original one that they gave me, 6, 2. I now know what this one is. I now have the components 2, negative 2. So by subtracting those two, I'll get the components of this vector. So subtracting those two, I get 4, 4. So I can write this vector here as the sum of u1, which is the projection vector, which is 2, negative 2, plus the orthogonal vector, 4, 4. And you'll notice that when I get that and I add those together, 6, 2, I do get the original vector that I began with. Okay? So I know that's a lot to remember, a lot of information. The main thing to remember is you calculate or determine the projection vector by this formula here, and again that gives me this, and then this vector is the sum of this and the orthogonal vector here. Those two added together give me the original. So with a little bit of algebra I can determine what this one is. So let me walk through one more problem where we find the projection of a vector and then decompose it into a sum of orthogonal vectors. So we have the vector u, which is negative 8, 3. So a quick sketch of that, if I go negative 8 and up 3, you know, looks something like this. So this would be the vector u. And then we have the vector v, which is negative 6, negative 2. So over here, negative 6 and negative 2. And so we have this. So this is vector v. Now, the projection of u onto v would be if I draw a perpendicular line from this vector down to here. And so what I want to find is the length from here to here. This red vector is the projection of u onto v. And so what I want to know is what are the components of this projection vector. Now, this projection vector, along with this vertical line, which is another vector, these are orthogonal vectors. And if I take the components of the red vector, which is the projection vector, so if I took the components of that, and this is the projection of u onto v, and I added that to the orthogonal vector, which would be the green one. okay, if I added those two together, that will give me the u vector. Okay? This is called decomposing a vector into its perpendicular components. Okay? So this red vector plus this green vector will equal this yellow vector. Okay, so what I need to do is to determine the red components, and that is the projection of one vector onto another. So the projection of the u vector onto the v, remember the formula is it's the dot product of the two vectors over the magnitude of the v vector squared, the one that's being projected onto. If we then multiply that by the components of that v vector, that's going to give me the projection vector. Okay, so we multiply or do the dot product of the u vector times the v. Remember, to do the dot product, I multiply the a components, so 6 times 8 is 48, or negative 6 times 8 is 48, plus 3 times negative 2, so it's actually negative 6. All right, over the magnitude of the v vector, the magnitude of the v vector squared, you can remember, is the square root of the a component squared plus the b component squared, but because I'm squaring it, I can simply square the numbers and add them together. So 6 squared is 36, plus 2 squared is 4, so that would be over 40. And then I'm going to multiply that times the components of the v vector. Okay, so 48 minus 6 is 42 over 40, and then I can reduce that dividing both by 2, so that's 21 over 20 times this v components will give me the projection vector components. So multiplying this scalar here for the a component, the 20 and the 6 are both divisible by 2, so that's going to make this a 3, so that's going to be negative 63 over 10. And then multiplying it by this, the 2 and the negative, the 20 and the negative 2 are both divisible by 2, so that's going to give me then a negative 21 over 10. So these would be the components of this vector here. What I need to figure out now are the components of this vector that's perpendicular to it. And I know that this plus this is equal to this, so I know what the red components are, the projection vector. I know what the original components are, the yellow vector, so a little bit of algebra manipulation, meaning I simply take the original vector minus the projection vector, that's going to give me this perpendicular vector. So I simply need to take the u vector, which is negative 8, 3, and then I need to subtract the projection vector of negative 63 over 10 and negative 21 over 10, and by subtracting those, that's going to give me the components of this original or this other vector. So in order to add these, I'll need a common denominator. So this is going to be negative 80 over 10, and this will be 30 over 10, and then I'm going to subtract it from this projection vector. And that will give me then the components of this perpendicular vector. So negative 80 minus a negative 63, or negative 80 plus 63, so that's going to be what? Negative 17 over 10 will be that component. And then 30 minus a negative 21, or 30 plus 21, is going to be 51 over 10. So this is the projection vector. This is the vector which is perpendicular or orthogonal to it. Those two added together should equal my original vector of negative 8, 3. So my original vector of negative 8, 3 should be equal to the projection vector of negative 63 over 10, negative 21 over 10, plus its perpendicular or orthogonal vector of negative 17 over 10 and then 51 over 10. And this should be simple enough to check. I'll just simply add these together and I should get my original vector. So negative 63 plus a negative 17, that's negative 80 over 10, which is negative 8. And then negative 21 plus 51, negative 21 and 51 is a positive 30 over 10, which reduces to 3. So these are the two perpendicular vectors, or orthogonal vectors, one of which is the projection of u onto v, and together, if we add them together, we get our original vector. So this is how you determine the projection of one vector onto another. We remember this formula right here, so this is going to be something you'll need to remember. And then this is how we decompose a vector into the sum of two orthogonal vectors, one of which is the projection of one vector onto another.